The next common type of structure in organic molecules is the skeletal structure. Unlike the condensed structure, the skeletal structure shows the bonds between atoms, but it specifically omits all carbons and hydrogens in its structure. Here's the Lewis structure for hexane, which is a 6-carbon molecule, showing all the bonds and atoms in the structure. But in its skeletal structure shown here, all the carbons and hydrogens were removed, and what's left are the bonds. You can see the same concept here for cyclohexane. So this is the Lewis structure for cyclohexane, and this is its skeletal structure. And as you can see, all the carbon atoms and hydrogen atoms in this molecule are omitted. So let's take a look at this one example shown here. It says, draw in all carbon atoms, hydrogen atoms, and lone pairs in the following molecule. So the first thing that you want to do here is to place a carbon atom at the intersection of any two lines and at the end of any line. So when you look at this structure shown here, you can see that you have intersections between two lines, right? So this is one line, second line, and this is the intersection. So that means that you have a carbon atom here, another carbon here, up here, down here, and up here. And then it also says place a carbon atom at the end of any line. So that means that there's a carbon atom right over here at the end of this line. There's not going to be any carbon atom here because this end of the line contains oxygen and hydrogen. And so now we've drawn in all the carbon atoms for each intersection and at the end of any line. The next step is to add enough hydrogens to make each carbon tetravalent. So what that means is that each carbon atom should contain a total of 4 bonds because each bond contains 2 bonding electrons. So if you have 4 bonds, that's a total of 8 bonding electrons, which satisfies the octet rule. And so now we have these carbon atoms shown here. And so looking at this first one here, this carbon only has 1 bond. And so you're going to add 3 hydrogens bonded to this carbon in order for it to become tetravalent. This carbon over here is double bonded to an oxygen. And so it already contains a total of 4 bonds. You have a double bond and 2 single bonds for a total of 4 bonding electron pairs. So this satisfies the octet rule. And then we have this carbon over here, which is double bonded to this carbon. And so this one is missing 1 other hydrogen, 1 other bond. And then this one, the same thing, 1 hydrogen bond. And then we have this carbon in green. And you can see that both of them only contain 2 bonds. And so they're missing 2 other bonds to become tetravalent. And so you would attach 2 hydrogen atoms for these 2 carbon atoms. So now we have the Lewis structure for this molecule. And the last step here is to add lone pairs to give each heteroatom an octet. So if you remember, a heteroatom is basically any atom other than carbon and hydrogen. So these oxygen atoms are considered heteroatoms. And so when you look at this oxygen right here, you have to add 2 lone pairs in order for it to have a total of 8 electrons, satisfying the octet rule. Same thing for this oxygen right here. So it has a single bond to this carbon and another single bond to that hydrogen. And so by adding 2 lone pairs, you would be satisfying the octet rule. So let's take a look at a few more examples here. So we have 2 skeletal structures, and let's convert them into normal Lewis structures. So the first step here is to basically analyze the structure, and we're going to add carbon atoms in every 2 intersections, 2 intersecting lines. So there's a carbon here, 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 and here. And then we're also going to add a carbon atom at the end of each line. So basically this one right here has a carbon atom. All right, so let's draw these carbon atoms in. So we have carbon here, 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 which basically makes a hexagon. And then we're going to connect them all together. And then on this carbon, there's another carbon that's connected to it. And that's basically the end of the line. And then there's another carbon connected to this carbon in blue. And then to this carbon is nitrogen. So you have nitrogen connected to it, and then 2 hydrogen atoms connected to the nitrogen. All right, and then we're going to complete the octet for each carbon atom by adding enough hydrogens. And so for this carbon, it contains 2 bonds, and in order for it to become tetravalent, we have to add 2 more bonds. So we're going to bond 2 hydrogens to this carbon, and every carbon in this ring, basically. So we're going to add 2 carbons here, 2 hydrogens here, here, and here. All right, so when you look at these 2 carbon atoms here, you can see that they already have 3 bonds. So they're only missing 1 other bond, which would be for hydrogen. And then for this carbon atom, it has 2 bonds, and so we're also going to add 2 hydrogens to it. All right, and the last carbon is right over here. It only has 1 single bond, and in order to convert this into a tetravalent, we're going to have to add 3 bonds, 3 hydrogen atoms bonded to it. So now all carbon atoms contain 8 bonding electrons, a total of 8 electrons, which satisfies the octet rule. But then when you look at this nitrogen right here, it only has 3 bonds, which means that it only has 2, 4, 6 electrons surrounding nitrogen. And so in order to satisfy the octet rule, we have to add a lone pair of electrons on the nitrogen. So now it satisfies the octet rule. So in this second structure here, we have a triple bond. So that means that there's a carbon here that's triple bonded to another carbon, and this carbon is single bonded to another carbon. So each end of the line contains a carbon atom. So you have a carbon that's triple bonded to another carbon, and each carbon is single bonded to 1 carbon atom. And so that means we have a total of 1, 2, 3, 4 carbon atoms in this structure. And then each carbon atom should be tetravalent. So these 2 central carbon atoms, are already tetravalent. And so looking at the end carbons, you can see that they are not. So we're going to add 3 hydrogens to each end carbon atom. And that's it. So this is the Lewis structure for this molecule. Here's practice problem number 23. How many hydrogen atoms are present around each highlighted carbon atom in the following molecules? What is the molecular formula for each molecule? Both compounds are active ingredients in some common sunscreens. So we have octane oxate and avobenzone. So let's look at this first molecule here. So it's asking for the number of hydrogen atoms bonded to each highlighted carbon atoms. So with this one right here, you can see that it only has 1 single bond. And so in order for this carbon to be tetravalent, it has to have 3 hydrogens attached to it. So we're just going to draw in a carbon here that's single bonded to this oxygen. And so that means that it has to have 3 hydrogens bonded to this carbon. All right, and what about this carbon atom here? So there's a carbon here, and this carbon is double bonded to this carbon. So I'll just put another carbon here. And this carbon atom is single bonded to this carbon here, and then single bonded to this carbon as well. All right, so you can see that this specific carbon atom already has 4 bonds because it's double bonded to this carbon. It's double bonded to this carbon, single bonded to this carbon, and then single bonded to this other carbon. So this carbon has a total of 4 bonds, 4 bonding electron pairs. So there's no hydrogen connected to it. What about this carbon here? So this carbon is double bonded to this carbon atom. And so we're going to add a carbon here just to show that, and then double bonded here. So right now, this carbon has a total of 3 bonding pairs. And so in order for it to have a total of 4 bonding pairs, we can add a hydrogen to it. So we'll bond 1 hydrogen here. And then for this last carbon atom here, we have a single bond here, and another single bond. So in that case, it's not tetravalent, and by adding 1 hydrogen to it, makes it tetravalent. All right, so now the second question here is, what is the molecular formula for each molecule? So in order to answer this question, the very first thing that you want to do is to analyze this structure and write down the elements that are present in this structure. So as you can see, we have carbons, hydrogens, and oxygen. So that's the first thing that you want to do, is write down the elements that are present in alphabetical order. Okay, so we have CHO, alphabetical order. And then count the total number of carbon atoms, total count of hydrogen and oxygen. So here it's easy to count the total number of oxygen atoms. So we have 1, 2, and 3. So we're going to put 3 as a subscript. All right, so that indicates that we have a total of 3 oxygen atoms. Now for carbon, you would have to draw in all the carbon atoms. So we have carbon here, here, another carbon here, carbon here, and here. All right, and then recount the total number of carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have a total of 18 carbon atoms. And you can double check that if you like. And then we're going to put in all hydrogens connected to these carbon atoms that we just labeled. And so looking at this carbon over here, this carbon has a single bond and then a double bond. So that means that it will have 1 hydrogen connected to it. So there's this carbon right here, 1 hydrogen here, 1 hydrogen here as well. And so when you look at this carbon atom here, it's already tetravalent because it has 1, 2, 3, 4 bonding electron pairs. This carbon over here has 3 bonding pairs. So it's missing 1 hydrogen here. This carbon is already tetravalent as well. This carbon is not. So it contains 2 hydrogen atoms. And then this carbon right here needs 2 other hydrogen atoms. And then this carbon has to have 3 hydrogen atoms. Let's see. This carbon needs 2 other hydrogens. This carbon atom, as well as this one, needs 2 other hydrogen atoms. And then the end carbon here should contain 3 hydrogen atoms. All right, so now we can count all the hydrogen atoms here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. So this is the molecular formula for this molecule, C18H26O3. All right, so what about this next molecule here, avobenzone? So first, label all the carbon atoms. So we're going to label carbon here. All right, so we've labeled all the carbon atoms, and then you want to make sure that each carbon atom is tetravalent. So we're going to go ahead and label the hydrogens as well. And here's all of the hydrogen atoms bonded to each carbon atom. And again, you can always double check this to make sure that every carbon atom is tetravalent. And so now let's count the total number of hydrogen atoms. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. So there's a total of 22 hydrogens, and the elements present are carbon, hydrogen, and oxygen. And I think we counted 22 hydrogens, and then for the oxygens we have 1, 2, and 3 oxygen atoms. And then what about the carbon atoms? So let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 carbon atoms, 22 hydrogen atoms, and 3 oxygen atoms. So this is the molecular formula for this molecule. And then it's asking the total number of hydrogen atoms in the highlighted carbons. And so here's a highlighted carbon. It only has 1 hydrogen attached to it. And this other highlighted carbon has 0 hydrogen atoms. This carbon has 0 as well. And then this last one has 3 hydrogen atoms attached to it. And here's practice problem number 24. Convert each skeletal structure to a complete structure with all carbons, hydrogens, and lone pairs drawn in. All right, so the first thing that you want to do here is to draw in the carbon atoms, followed by the hydrogens, and then the lone pairs. Okay, so looking at this first molecule here, there's a total of 4 carbon atoms that are connected to form a square. So you have 4 carbon atoms, 1, 2, 3, and 4, that are connected together to basically form a ring. So this is called a ring. Any closed loop is a ring, basically. All right, and then this carbon here is connected to 2 other carbons. And then now we have to put in all the hydrogen atoms to make sure that every single carbon atom is tetravalent. So let's start with this carbon up top on the left. It has 2 hydrogen atoms bonded to it. This carbon is already tetravalent, and so we don't need to add a hydrogen to it. But these end carbons will contain 3 hydrogen atoms. And then both carbon atoms here at the bottom will contain 2 hydrogen atoms. All right, and that's basically the Lewis structure, the complete structure for this molecule. Okay, so what about this second structure shown here? So we have carbon here that's connected to the oxygen atom. So each intersection contains a carbon atom. So carbon here. All right, and then we want to make sure that each carbon atom is tetravalent. So we're going to add 2 hydrogen atoms to each carbon atom. And then finally, any lone pairs. So this oxygen right here doesn't have an octet, right? So it only has 2 bonding pairs. So that means that we're going to need to add 2 lone pairs on this oxygen atom. So now when you count the total number of electrons, it has 2, 4, 6, 8. And in this structure, we have end carbons here. So we have 1, 2, 3 end carbons, and then the middle carbons. All right, so let's label these carbons real quick. 1, 2, 3, 4, and 5. And then everything else is hydrogens and nitrogens. And so we have carbon that's bonded to a nitrogen, and this nitrogen is bonded to 3 carbon atoms. And then you have another carbon atom here that's bonded to a nitrogen. Let me move this to the left real quick. And then this nitrogen atom is bonded to a hydrogen, or a carbon atom. So now we've labeled all the carbon atoms. And now we're going to include the hydrogens. So making sure that every carbon atom is tetravalent. All right, so now we have all the hydrogens bonded to the carbon atoms. And now we have to look at the heteroatoms and make sure that they have a complete octet. So looking at this first nitrogen here on the left, you can see that it only has 3 bonds, and so it's missing a lone pair. Same thing with this nitrogen right here. It has 3 bonding pairs. It's missing a lone pair. All right, so this is the Lewis structure, complete structure for this molecule. So now let's take a look at skeletal structures with charged carbon atoms. Any carbon with 1 less bond and no lone pair will have a positive charge. So when you look at this carbon atom here, it has 3 bonds with no lone pair. So using the equation regarding formal charge and the concept of formal charge, you'll be able to determine that there is a positive charge on this carbon atom. On the other hand, any carbon with 1 less bond and 1 lone pair will have a negative charge, as shown here. So when you look at this carbon atom, you can see that it has a lone pair and 3 bonding pairs. And so when you apply the formal charge equation, this carbon atom will have a negative charge. When it comes to skeletal structures involving heteroatoms, the lone pairs are generally omitted. But you have to remember that they do exist, just like the omitted carbons and hydrogens. So let's look at a few examples here. So here's a molecule, the skeletal structure of an alcohol. And you can see that the heteroatom oxygen doesn't show any lone pairs. But when in reality, it actually contains 2 lone pairs of electrons. And you can always double check that each heteroatom follows the octet rule. So now this oxygen has 2 bonding pairs, and so in order for it to follow the octet rule, it has to contain 2 lone pairs of electrons. Same thing over here for this charged oxygen. So this actually contains a lone pair of electrons. So you can see that this oxygen currently has 3 bonds or 3 bonding electron pairs, and it's missing a lone pair in order for it to have a complete octet. Here's practice problem number 26. Draw in all hydrogens and lone pairs on the charged carbons in each ion. So if you remember, a carbon with a positive charge has one less bond and 0 lone pair. Whereas a carbon with a negative charge, it has 1 less bond and 1 lone pair. So this actually has a lone pair. So when it says 1 less bond, it means 1 less bond compared to a tetravalent with 4 bonds. So when you look at this first carbon over here, this has 3 bonds, which means it's 1 less bond. And because it has a positive charge, then that means that it doesn't have any lone pair. And because it already has a total of 3 bonds, it won't have a hydrogen attached to this carbon. All right, so no hydrogen attached to this carbon. What about this second one over here? So because this has a negative charge, that means it has 1 less bond and 1 lone pair. So when you look at this carbon, so I'm just going to draw in this carbon. So this carbon basically looks something like this. So you have a carbon that's bonded to these carbons here, the end carbon, and a lone pair. So that means that it has 1 lone pair and another bond, which would be a hydrogen. All right, so this carbon, this charged carbon right here, has 1 lone pair and a hydrogen bonded to it. All right, what about this third one here, a positive charge? So again, this carbon looks something like this. So you have a carbon that's a positive charge bonded to 2 other carbons and so on. I'm just going to remove that. All right. And so again, a positive charge means that you have 1 less bond and no lone pair. So that means that it has another bond here, and that would be bonded to a hydrogen atom. All right, and what about this last one, or part D here? A carbon that's bonded to two other carbons. So that means that it has a lone pair and another hydrogen bonded to it. So this specific carbon has 3 single bonds and 1 lone pair, and that's why it has a negative charge. All right, and the last one here. So we have a carbon that's triple bonded to another carbon with a negative charge. So in order for this carbon to have a negative charge, it must have 1 lone pair and no hydrogen atom bonded to it. And that's it. And here's practice problem number 27. Use the formal charge to draw in the lone pairs on each nitrogen or oxygen atom in the following compounds. All right, so let's look at this first one over here. So we're only looking at the hetero atoms, nitrogens and oxygen. And so looking at this nitrogen here, in order for it to have a positive charge, so remember that the formal charge is equal to the number of valence electrons of that atom minus the number of electrons that atom owns. All right, and so for this nitrogen right here, it has a total of 5 valence electrons, and the number of electrons it owns is basically 4, right? 1, 2, 3, 4, because 2 electrons here are being shared, half of it that nitrogen owns. So a total of 8 electrons divided by 2, and you have 4 electrons owned by this nitrogen. So 5 valence electrons minus 4 that it owns leaves 1, which is the positive charge. And so it says use the formal charge to draw in the lone pairs on each nitrogen in the following compounds. All right, so no lone pairs here, but for this specific nitrogen, in order for this to have a neutral charge, as it does now, it should have a lone pair. All right, so the number of valence electrons is 5 for this nitrogen minus a total of 5 owned by this nitrogen equals 0. All right, what about for B? So for the second one here, we have a nitrogen with a negative charge. And so that means that the number of electrons owned by this nitrogen must be 6, right? 5 minus 6 equals a negative 1 charge. And so right now it has 1, 2, and then it needs 4 more. That means you can just put 2 lone pairs here for a total of 6 electrons owned by this nitrogen. So this is the complete structure for this molecule, having 2 lone pairs on the nitrogen. All right, so what about this third structure here on the right? So we have nitrogen with a positive charge, and then these oxygen atoms right here. So this oxygen doesn't have a complete octet, okay? So it has 2 bonds, a double bond, which equates to 4 bonding electrons. And so in order for this to have a complete octet, you would have to add 2 lone pairs. So this oxygen has 2 lone pairs with a 0 formal charge. This oxygen has a negative formal charge, so that means that again, if you just want to look at the number of electrons surrounding oxygen, it should have a total of 8, and so it's missing 3 lone pairs. So you can use octet rule as your basis, or you can use the formal charge as your basis to determine how many lone pairs you would add onto these atoms. All right, and the last one here, we have oxygen and the nitrogens. And so this oxygen right here would also have 2 lone pairs to satisfy the octet rule. And then this oxygen, this other oxygen would have 3 lone pairs to satisfy the octet rule. This nitrogen right here won't have any lone pairs. because it has a total of 4 bonds already. And so it would have a positive formal charge. And that's it. And here's practice problem number 28. Draw a skeletal structure for the molecules in parts A and B and a condensed structure for the molecules in parts C and D. Alright, so let's take a look at this first one here. So we have a CH3. That means that the carbon is bonded to this oxygen, and this oxygen is bonded to a carbon, and we have 2 repeating units of CH2s, and then the second carbon here is bonded to this carbon, and this carbon is bonded to this oxygen, and then this carbon is also bonded to this carbon that is double bonded to this carbon here, and we have 2 CH3s bonded to this carbon, 2 units of CH3s. All right, so let's take a look. So we have a CH3 bonded to an oxygen, and then we have 2 repeating units of CH2, and then the second CH2 is bonded to a carbon, and that this carbon is bonded to an oxygen, and then this carbon is also bonded to this carbon, and that carbon is bonded to a hydrogen and also double bonded to another carbon. So here's a hydrogen and double bonded to a carbon. And then finally we have 2 groups of CH3 bonded to this carbon. So one CH3 here and then another CH3 here. All right, so let's analyze some of the atoms here. So this oxygen needs to have a complete octet, so that means that it has to have 2 lone pairs. So that satisfies the octet rule. This carbon right here only has 3 bonding pairs, so it lacks 2 bonding electrons. But if you form a double bond with this oxygen, which also lacks an octet, that would satisfy the carbon would satisfy the octet rule. This oxygen only has 4 bonding pairs, so it lacks 2 lone pairs. And now its octet is completed. So the question here is draw a skeletal structure. So this basically is the Lewis structure, and now we have to turn this into a skeletal structure, not showing the hydrogens or the carbons. So we have an oxygen with 2 lone pairs bonded to a carbon and then another carbon here. Okay, so we have 1, 2, 3, 4. So again, we're just counting from here. So we have 1, 2, 3, 4th carbon, and then another carbon that's bonded to this carbon, and then this carbon is double bonded to another carbon with 2 CH3 groups. All right, and then all you have to do now is connect the dots. And then don't forget that we have a carbon here that's double bonded to an oxygen. So which carbon is that? So we have a carbon double bonded to a carbon. So here's a carbon double bonded to a carbon, and then single bonded to this carbon that's double bonded to an oxygen. So we're going to put a double bond here to an oxygen. And then 2 lone pairs. All right, so that would be the skeletal structure for A. All right, so what about this second one here? So this one is a little bit easier because you basically already have the backbone drawn in. So you have a carbon that's connected to this carbon. So I'm just going to circle all the carbon atoms here. And then I'm going to connect them together using a bond. Right, so connect here, here. So this is basically a square. And then another carbon bonded to another carbon. And then that carbon is connected to a chlorine atom. So now we can draw in the backbone. So we have 1, 2, 3, and 4. Connect them together. And then we have a CH3 connected to this top left corner carbon. And then 2 carbon atoms attached to this carbon. So we have 1 and 2. And then the second carbon is connected to a chlorine atom. And that chlorine atom should have 3 lone pairs in order to satisfy the octet rule. All right, and then we have, so again, the hydrogens that are bonded to the carbon are emitted. Same thing with the carbon atoms. But for the nitrogen, we have nitrogen here. And you can just leave it as NH2 with a lone pair on the nitrogen. All right, so what about part D? So it's the same concept. You're going to label the carbon atoms first. And then include the hydrogen atoms. So we have all the N carbons with 3 hydrogen atoms. And you want to make sure that every single carbon atoms remaining here has a tetravalent, meaning 4 bonds. So this carbon right here will have 2 bonds, this carbon 2, and these 2 carbon atoms will have 1 hydrogen bonded to it. And then finally this carbon would have 1 hydrogen bonded to it as well. All right, and so now we can condense this further. So we have an HO here that's bonded to a CH2 and then another CH2. So we can group this together. And then this carbon is bonded to this carbon that's double bonded to another carbon. So we have a CH and then a double bond to another CH. And then we have another carbon that's bonded to 2 oxygen atoms. So that would be CO2. And then a CH. Let me create some space here. And then finally, this carbon atom has 2 CH3 groups bonded to it. So CH3, 2. Now we can get rid of the bonds, except for maybe this double bond right here. So you want to specify that the 2 carbon atoms are double bonded together. So now we have HO parentheses CH2 in parentheses, and then the subscript 2 followed by carbon hydrogen double bond to another carbon hydrogen. And then CO2 CH parentheses CH3 and then 2 outside. And this is the condensed structure for this molecule.